So we've been talking about all the different types of plate boundaries, right? Convergent, divergent, and transform, and focusing on the features that each one has on Earth to tell us what's going on inside the Earth. But we haven't totally discussed how is this happening in the first place? What's going on inside the Earth to make us see these features on top and to allow the crust to move in such ways? So we've got two essential questions that we're working on today. One of them, we want to be able to describe how convection currents make the motion of our tectonic plates happening on the Earth's surface. And as we do that, we want to put in our two key words of the day. We want to add in the words ridge push, and we also want to add in the words slab pull. Okay, again, those will be our key words of the day. We also want to know, by definition, not only what those words are, but also what type of plate boundary is apparent when we hear those two key words. So again, our two essential questions or focus for this discussion today. So before we can figure out how the plates are moving, we got to know a little bit about what's going on inside the Earth. And there's three main forces happening inside the Earth that cause the motion of the plates on the surface. The first one here is called convection currents. Okay, convection currents, we see that happening inside the Earth. And within that convection current, there's two key things we're going to look for. Something called ridge push, and also something called slab pull. Again, our three key forces happening inside the Earth that make plate motion. So what is convection? I'm hoping that you've heard the word convection before. Okay, it is the circulation of material caused by a difference in density. Okay, density, of course, talking about the mass of the material, heavier or lighter. Now, convection, you've seen a few different places. One, I know that you've experienced convection is within your home. Right? In your home, you have a little furnace, and we typically see the furnace found down here in the basement. There it is, the furnace, and the furnace's job is to heat your home. So it sends out hot air from the furnace, and we've all heard the phrase before that hot air rises. So that material rises up, warms the upper layers of your home, and when that air is far away from the furnace after a while, it starts to cool down, and then it sinks back down towards the basement where it comes in contact with the furnace, heats back up, cools back down, heats, and circles. This is convection. Okay? A couple other places that we've seen or experienced convection is the atmosphere. Okay, atmosphere, we have warm and cool air currents moving air around the atmosphere. Same thing within the ocean. Okay, so that material within convection can be air, can be water. In your home, of course, it's air. Also in the oven. Okay, it is air. If you've ever looked inside your oven, you might have the type of oven with the little coil on the bottom, right? That heats up and get warm while you're cooking your little Hot Pockets or pizza rolls, right? The warm air comes up, heats up, stays away from the heater, cools down a little bit, reheats and keeps cycles, and then your little light comes on when the oven is hot enough and ready to go. So convection is all around us. We're looking at today, of course, convection in the mantle. Okay? Not only in the mantle, but especially we see it in the asthenosphere. Right? That is the upper part of the mantle, our plastic-like layer. And because that layer moves a little bit, it helps move the layer above it, which we know as the lithosphere. Lithosphere is the lower part of the crust, asthenosphere being the top part of the mantle. And as the asthenosphere moves, the lithosphere resting on top then moves with it. Because essentially, the lithosphere is just floating on the asthenosphere, kind of like a boat sits on the water. I've got my river, whatever it is. Got my boat sitting on top of there. If the water has a current to it, that boat is going to move right along with it. We basically see the same thing here with the lithosphere and the asthenosphere. Motion in that lower layer drives motion of that upper layer. Okay, so our convection, we notice that we've got hot mantle material rising upward. And that's all because of that density current. Because that hot mantle material becomes less dense, it rises upward and comes in contact with the underneath of the Earth's crust. Right? You can see that in this little picture here. As that material works its way up through convection, it comes in contact with the bottom part of the Earth's crust. And I'd like it if you could grab out a color, like a pink or a red or something, and just go ahead and shade in that area with a red arrow, reminding us this is our warm material. And then we know that material can't stay warm forever. It does have to cool down, and when it cools down, its density changes, and it becomes more dense and sinks. Oops. Right? And this whole process of warm material rising up, cool material sinking down, that whole process, that entire cycle, is what we know as the convection current. Okay, so make sure you get your colors out. For sure, label them if you can. Color code them with the red warm and the cool bluish color. Now we can really see this convection happening in that lower picture on your paper. We've got the full cycle of convection right here. I've got the warmer material rising up, the arrows moving their way up. And of course here I've got my cooler material sinking down. Okay, now what is it that's heating up that material in the mantle? We know the furnace heated the air in the home. We know the sun heats the air in the atmosphere and the water in the ocean. But what is it here inside the earth that drives that convection current? It's all down here in the core, right? We know the further down in the earth we go, the hotter that material gets. Now the source of all this heat is a certain material in the core that is radioactive. That radioactive material, of course, within the Earth's core is warm and toasty. And the heat from that is transferred to all the other layers, working its way up through the mantle and the asthenosphere. So the heat transfers here, causing material to rise and sink within that convection. So again, I want you to take a second, pause the video, answer that question at the bottom. How is that convection inside the mantle really moving the plates on the Earth's surface? Think about what we talked about for the asthenosphere and the lithosphere. Go ahead and pause and see if you can jot an idea down there. Okay, as we flip to the back side here, we're talking about now the two parts of the convection current that really relate to the two boundaries we see on the Earth's surface. Those two parts of the cell are called ridge push and slab pull. Okay, we'll start with ridge push here. Ridge push happens when I have rising mantle material making the potential for plates to move away from a ridge. Now this force, of course, you would guess, is called ridge push, right? Because what's happening here is I'm having material pushed away from a ridge. So this is the top part of the convection current where I have that warm material rising up from the heat of the inner core and the outer core. As that warm material rises up and hits the bottom of the crust, it has nowhere to go. So it automatically starts to divide out and I get a little ridge that forms on the Earth's surface. Okay? As that ridge starts to form and becomes higher in elevation, I start to see gravity take over a little bit. And so what gravity does is it starts to pull the surrounding rocks a little bit down and away from that ridge. creating what we know as a divergent boundary, right? Again, looking at the image, this is where we see our warm convection material rising up, reaching the bottom of the crust, and starting to push that material out. This is all happening here in the asthenosphere. Right? This is the top part of the mantle. Okay, so this is the asthenosphere. It's the plastic-like layer. The lithosphere sits right on top. So because the asthenosphere moves, the lithosphere, which rests on top, is automatically going to move with it. So of course, the type of boundary that we can expect to see here would be a divergent boundary. Go ahead and label this in. Type of boundary we expect to see here is a divergent boundary. The arrows to represent that boundary would, of course, go in opposite directions. This is what we see on Earth. So what big time feature would I have right here? I would, of course, have my mid-ocean ridge. Because I have magma being pushed up from inside the Earth, I would also have a rift valley. Two key features paired with divergent boundary because of convection and this whole process called ridge push. My second process here called slab pull. Okay. In other parts of the convection current, I have cold, dense material starting to sink to get back to the heat coming from the core. So as that slab or dense plate starts to sink, what happens is it then pulls the rest of the plate with a force called slab pull. Okay, and again, it's all in the name. The ridge is being, or the rock is being pulled now by slab pull. We saw the ridge pushing the rock, ridge push. Now we see the slab being pulled by slab pull. So the cold, dense mantle starts to sink down. Again, because we're talking about the asthenosphere here. We're talking about movement in this layer causing movement of this layer on top. So doing the same thing as we did here, as that cold material is sinking in, we can expect to see subduction here, which of course is leading us to our convergent boundary. Okay, convergent boundary because of our subduction here. This plate's being pulled down. Over here I would have the same exact mirror of a convection current because they happen all within the mantle. So I've got it happening all around. So this side would be pushed towards this side, giving me my convergent boundary. Adding in a couple key features here, we've already said subduction zone. Okay, we also know with every subduction zone, we're going to have a trench. Right? Deep ocean trench happens right where those two plates meet. As that plate gets pulled down and starts to melt, that's going to bring magma to the surface, making my volcanoes. Right? All kinds of features, again, happening simply from the convection within the mantle. Okay, now you have a diagram here to finish your thoughts. Start finding places to label the following terms on the diagram. Some of them are pointed out here with the little arrows. You can use some of those to match up, but others you can just write in on the diagram. We can see the mantle is already labeled here, so we can go ahead and cross that one off from our list. We're good to go. But find a spot for the other terms, either, again, on those arrows or within the diagram. Okay? Once your diagram is labeled, you do want to end by answering these two essential questions. It is important that you use the terms ridge push and slab pull when you go to talk about convection currents and the motion of the plates. Talk about the type of boundaries connected with those, right? And that'll come up here again in number 2.